Today I'm gonna present my assignment, University Physics with Modern Physics. And I'm gonna present three physics problems from chapter 11. So first things first, please subscribe to my YouTube channel. As you can see, there's no background color right now. There's no PowerPoint design because I ran out of funds and I really need the money, man. Para yeah. Anyways, let's move on with the first problem. So, Erlach's biceps requires a force of 25 newton for an elongation of 3 centimeters. The same muscle under maximum tension requires a force of 500 newtons for the same elongation. Find Young's modulus for the muscle tissue under each of these conditions. If the muscle is assumed to be a uniform cylinder with a length of 0.200 meters with a cross-sectional area of 50.0 centimeters squared. So, your given is cross-sectional area, which is 50.0 centimeters squared, which is 0.05005 meters squared. The force perpendicular when it's relaxed, which is 25 newtons. The force perpendicular when it's on maximum tension, which is 500 newtons. Change in no, change in length of the biceps or the elongation, which is 0.03 meters or 3 centimeters, and the initial length, which is 0.200 meters. All you have to do is find Young's modulus. Now, Young's modulus equals to times force perpendicular times I times LO over cross sectional area over change of L. So it'll be simple. Just plug in all the values. So for the relaxed one, since it requires less force, that means that it has a smaller Young's modulus, which is a 3,333 PA. And for maximum tension, all you have to do is plug in everything, and you get 6,667 PA. Anyways, now let's move on to the even harder question. So a 72.0 weightlifter doing arm raises holds a 7.50 kilogram weight. Her arm pivots around the elbow joint starting 40 degrees below the horizontal. Biometric measurements have shown that together, the forearms and hands account to 6% of the person's weight. Since the upper arm is held vertically, the biceps muscles always acts vertically and is attached to the bones of the forearm, 5.50 centimeters from the elbow joint. The center of mass of this person's forearm hand combination is 16.0 centimeters away from the elbow joint, along the bones of the forearm, and she holds the weight from her elbow joint. So, let's first find out the given. So this is the diagram of the entire thing. So the biceps muscles, the elbow muscles, the 30 the 38 centimeter distance from the center of mass of the weight, the elbow, and 7.50 kilogram weight. So all you have to do is draw a free body diagram to forearm, find the force the bicep exerts on the forearm, find the magnitude and direction of the force that the elbow joint exerts on the forearm, and answer the question. As the weightlifter raises her arm towards horizontal position, will the force of the biceps increase, decrease, or stay the same? And say why. So first up, here's a free body diagram. So there's no force acting along the x-axis. On the y-axis, there is a force and there is a work done from the elbow joint to B and elbow joint to C, which is, as you can see, it is mostly the 5.50 centimeter, which is from the forearm, from the elbow joint to the forearm, and the and the 16.0 centimeters, which is from the elbow joint to the forearm hand combination. Now, with all that said, the mass of the body is 72.0 kg, mass of the weight is 7.5 kg, and theta is 40 degrees. But is theta even relevant? Find out next time. We'll find out later. Weight of the forearms and hands accounts for 6% of the entire body weight, so the weight of the forearms and hands is 4.32 kg. A, or the distance between the elbow joint is 0.55 meters. From elbow joint to point B, it's 0.16 meters, and from elbow joint to point C, it's 0.38 meters. Now, what force does the biceps exert on the forearm? So, all you have to do is, since the arms and hands, since you have two arms and hands, you have to multiply it by 1/2 and just use the force of gravity, which is simply weight. So 1/2 4.32 kg times 9.8, you get 21.168 newtons, which is the force which is the force which is how much force the bicep exerts on the arms and hands, and the weight the person is lifting, which is 1/2 7.5 times 9.8 meters per second squared, or simply the weight, which is 73.5 newtons, and you get the force. Moving on from that, let's move on to the magnitude and direction of the force that the elbow joint exerts on the forearm. So, this the magnitude and direction of force, just the summation of torque. So there's no force acting over x, there's no force acting over y, pero there is a 40-degree force acting on A, B, and C, which should equate to 0. So all you have to do is multiply it. So 21.168 newtons, the first value you get, simply multiply it by the distance from the elbow joint. Same goes with the other. Multiply distance from the elbow joint to 73.5 newtons and divide it by 0.05, which is the distance from the elbow joint to first off, find what you're trying to find. Distance of the elbow joint to the forearm. Okay. Distance of the elbow joint to the forearm. Now, with all that said, once you manage to get the distance from the elbow joint to the forearm, you can now get the upward force, which is 5.39.38. It's upward because everything else is going downwards. Anyways, let's move on. As the weightlifter raises her arms towards the horizontal position, will the force in the biceps increase, decrease, or stay the same? Why? As you can see, we had theta, but we never really used it. So, yeah, it's really irrelevant in this equation. It's really irrelevant in this problem right now. Let's move on to the next. A therapist tells a 74-kilogram patient with a broken leg that he must have his leg in a cast suspended horizontally. For minimum discomfort, the leg should be supported by a vertical strap attached at the center of the mass of the leg cast system, as shown at figure 11.51, which I'll show later. To comply with these instructions, the patient consults a table of typical mass distributions. He finds that the upper legs, thighs, together completely account for 21.5% of the body weight, and the center of mass of the thigh is 18.0 centimeters from the hip joint. The patient also reads that the lower legs, including the feet, are 14% of body weight, with a center of mass of 69.0 centimeters from the hip joint. The cast has a mass of 5.50 kg, and its center of mass is 78.0 centimeters from the hip joint. How far from the hip joint should the supporting strap be attached to the cast? So, here's figure 11.51. So there's a hip joint, cast, and a supporting strap. So the mass of the injured person 7.74 kilograms. To find the upper leg, it's 21.5% of the total body mass. So multiply that by one half. Since you have two legs, you get 7.96 kg. Same goes for the lower leg, multiply it by 14% times one half and you get 5.18 kg. And the mass of the cast is 5.5 kg. So the center of mass of the upper leg from the hip joint is 18.0 centimeters. Center of mass of the lower leg from the hip joint is 69.0 centimeters or 0.69 meters. And center of mass from the hip joint to the cast is 78 centimeters or 0.78 meters. So the equation is mass of the upper leg, center of mass of the upper leg from the hip joint plus lower leg, center of mass of lower leg from the hip joint plus mass of cast and center mass of cast from the hip joint and mass of upper leg plus lower leg plus cast times x. Now you're trying to find x, which is where the supporting strap should be attached for maximum comfort. Now let's move on to the equation. Let's move on to plugging it in. So once you plug it in, just multiply everything. You already got the mass of the cast, mass of the upper leg, and mass of the lower leg, and their distances. So once you just multiply all of it, which is 7.96 kg times 0.18 meters plus 5.18 kg times 0.69 meters times 5.5 kg times 0.78 meters. Then divide it by the total summation of mass, which is 7.96 kg plus 5.18 plus 5.5 kg, and you'll get x, which is 0.499 meters. All you have to do is maintain unit consistency, and this chapter should be easy. Thank you.